So we are now in chapter 2, the EMF equation of a transformer. So we let N1 to be the number of turns in primary, N2 the number of turns in secondary, and also the flux M is the maximum flux in core in Webers, so that is equal to Bm multiplied by the area. So F is equal to the frequency of AC input in Hertz. So as shown in this figure, flux increases from zero value to maximum value of flux maximum, or this one, flux M, at this point. So this is your flux M at the frequency equal to the period over 4. Why 4? Because we have the degrees, 90 degrees, 180, 270, and 360 degrees. So, in 1/4 of the cycle, such that 1/4 of the frequency seconds. So, average rate of change of flux will be equal to the maximum flux divided by the 1/4 of the frequency. So, that is equal now to average rate of change of flux equal to 4 times the frequency multiplied by the maximum flux times the frequency. So now the rate of change of flux per turn means induced EMF in volts. So average EMF per turn is equal to 4 times frequency multiplied by the maximum flux in volts. So the unit of this average EMF is of course in volts kasi EMF siya. Now, rate of change of flux per turn means induced EMF in volts. If flux varies sinusoidally, then RMS value of induced EMF is obtained by multiplying the average value with form factor. So form factor is equal to the RMS value divided by the average value. That is equal to 1.11. Okay, so RMS value of EMF now per turn is equal to 1.11 times 4 multiplied by the frequency multiplied by the maximum flux, that is equal to 4.44 multiplied by the frequency times the maximum flux in volts. Now RMS value of the induced EMF in the whole primary winding is equal to the induced EMF per turn multiplied by the number of primary turns. So that is equal to E1 is equal to 4.44 times frequency N1 flux M. So as we have said earlier that this flux, maximum flux is equal to BMA. So E1, it is for the primary. Similarly, RMS value of the EMF induced in the secondary is E2 is equal to 4.44 multiplied by the frequency times this number of turns times the maximum flux. So it is seen from equation 1. This is our equation 1, E1. And equation 2 that since constant tong 4.44 frequency and maximum flux, we will get the E1 over N1 is equal to E2 over N2. So that is equal to 4.44 multiplied by the frequency times the maximum flux. It means that EMF per turn is the same in both the primary and the secondary windings. So the EMF per turn, so the voltage per turn at primary and secondary are equal. Okay? An ideal transformer on no load V1 is equal to E1 and E2 is equal to V2, where V2 is the terminal voltage or the output voltage. So voltage transformation ratio, K. So the designation of this voltage transformation ratio is K, or small letter A. Okay? So from equations I and II, we get E2 over E1 is equal to N2 all over N1 equal to K. So this constant K is known as the voltage transformation ratio. Condition 1, if N2 or the number of turns in secondary is greater than the number of turns in primary such that K is greater than 1, then the transformation is called step-up transformer. So, pag mas madaming number of turns yung nasa secondary mo dito versus yung turns ng primary mo, so it means the transformer is step up. Okay? Step up from V1 or E1 is step up na into E2. If N2 is less than N1 such that K is less than 1, then transformer is known as step down transformer. So if your number of turns in primary is greater than the number of turns in secondary, that means your transformer is step down. Just like in ENEC, we have in the transformer at the post, example is 6.9 kV, it will step down papunta sa bahay natin, which is 230. So the number of turns at this distribution transformer is larger or greater than the transformer here. The number of turns. So V1 I1 is equal to V2 I2. So V1 I1, it is equal to your apparent power. Apparent power 1 is equal to apparent power 2 at the secondary, or I2 over I1 is equal to I1 over V1 over V2 is equal to 1 over K. Example, a 25 kVA transformer has 500 turns on the primary and 50 turns on the secondary winding. The primary is connected to 3000 volts, 50 Hz supply. Find the load primary and secondary currents, the secondary EMF, and the maximum flux in the core. Neglect leakage drops and no load primary current. So given, we have the apparent power, which is the 25 kVA in the primary, and 500 turns N1 in the primary, N2 is number of turns in the secondary, which is equal to 50 turns. So we will try to solve the primary and secondary currents of transformer and also the maximum flux in the core. So we all know that apparent power is equal to the voltage multiplied by the current. V1 is the input, okay, input voltage, and S2 is equal to V2 I2. V2 here is the output voltage. Remember that this example is an ideal transformer because R and the inductance of the conductor is not given. So this is an ideal transformer. So we can solve first the primary current by this formula. S1 is equal to V1 I1. So I1 is equal to S1 over V1, 25,000 divided by 3,000, that is equal to 8.333 amperes. So E2, the EMF induced in the transformer, is equal to E2 over E1 is equal to the number of turns N2 all over N1. So that is equal to your constant K. Where your K is equal to, since given yung number of turns sa secondary and primary, we can solve your K, so that is equal to 0.1. Since this is ideal transformer, the induced EMF is equal to the input power, and the output power in the secondary is equal to the induced EMF in the secondary also. Okay, from our formula, kasi etong I1 is equal to E2, I2. E1 and E2 here are the induced EMF of the transformer, while V1 is the input voltage and V2 is the output voltage. So since this is ideal, E1 is equal to V1 and E2 is equal to V2. So we can equate this one. V2 all over V1 is equal to I1 over I2 by cross multiplying. Okay? So K is equal to V2 over V1 equal to 0.1 yung nasolve natin kanina dito. Okay? So we can solve now your I2. So K is equal to I1. This one, I1 over I2 is equal to 0.1. So from our equation kanina na, eto. Okay, since eto, E2 and E1 is equal to V1 and V2, and the apparent power in the primary is equal to the apparent power in the secondary in ideal transformer. Okay, wag kayong malito. So V2 over V1 is equal to I1 over I2. So K is equal to I1 over I2 is equal to 0.1. We can solve your I2. So I2 is equal to 83.333 amperes. Going back from our this one equation, V1 I1 is equal to V2 I2, we can now get your voltage at the secondary. So V1 kanina is 3,000 and our I1 is 8.333. This will be now your circuit in this problem. So this V1 is our input voltage, V2 is our output, E1 is the induced EMF in the primary, and E2 is the induced EMF at the secondary. So N1 number of turns in the primary and N2 is the number of turns in the secondary. I1 entering into the transformer, and this will be the mutual flux in the transformer. Okay, so V2 is connected to the load. Example number 2. A single-phase transformer has 400 primary and 1,000 secondary turns. The net cross-sectional area of the core is 60 square centimeter. If the primary winding be connected to a 50 Hz supply at 520 volts, calculate I. First is the peak value of the flux density in the core, or the BM. B, the voltage induced in the secondary winding. So we will calculate the BM, and the voltage induced is the E2. Okay, at the secondary. So we have here the given. So this is a step-up transformer, as you can see, because at the primary you have 400 turns. It is less than in the secondary. So we have 1,000 in secondary, so it will step up the voltage at the secondary. So N1, 400 turns, N2, 1,000 turns. Our area, big letter A, is 60 square centimeter. Frequency of the transformer is 50 Hz. So the given voltage here is the supply. So in ideal transformer, as we have said earlier in our discussion, that the input voltage in ideal is equal to the induced voltage in the primary winding. as well as in the secondary. Okay, so V1, input voltage, is equal to E1, the induced voltage at the primary is equal to 520 volts. So it is in ideal transformer. So required is the flux density, maximum flux density of the transformer, and the induced EMF, E2. So this is the circuit diagram of the transformer. We have the primary, 400 turns, secondary, 1000 turns, and the turns ratio between the primary and the secondary is the letter A or small letter K. So that is your turns ratio. So we have here the input voltage and the induced EMF at primary E1, and output voltage is the V2. Induced voltage at secondary is E2. This is ideal. So turns ratio A is equal to N2, the number of turns at secondary, divided by the number of turns at the primary. So that is also equal to the induced voltage at the secondary and divided by the induced voltage at the primary. So that is equal to 1000. So 1000 turns in secondary, 400 turns in primary. So turns ratio now will be equal to 2.5 volts. We can now solve the induced EMF at the secondary. So from this formula, A is equal to E2 over E1. So E2, you can solve E2 is equal to A E1. So 2.5 times 520 is equal to 1,300 volts. This is the induced voltage at secondary. So as you can see, the induced EMF at the primary is less than the induced EMF at the secondary because of the turns ratio. It is directly proportional. As the turns ratio larger, it will also result to a larger amount of voltage. So from our formula, E1, so we can solve BM at the primary and secondary. So dapat magkapareho yung makukuha mong BM sa primary and secondary. Of course, that is the same transformer, the same area yung ginamit na transformer. So dapat pareho yung makuhang BM sa E1 at saka sa E2 or primary and secondary. So let's try E1. E1 is equal to 4.44 multiplied by the frequency. So the frequency at primary and secondary are the same. Multiplied by the turns ratio N1 times BM times the area. So BM1 at primary is equal to E1 is 520 divided by 4.44 times 50 times 400 turns. 50 is the frequency times the area 60 square centimeter. Ang kailangan natin is square meter, so we'll convert this one into a meter. So 60 square centimeter multiplied by 1. So this is square. Multiplied by 1 square meter divided by 100 square. So that is 0.976 Weber per square meter. Let's try in secondary. So BM2 is equal to 1,300. This is our E2 divided by 4.44 times 50 times the number of ratio at the secondary, that is 1,000, times 60 square centimeter multiplied by 1 square meter divided by 100 square. It will result to the same 0.976 Weber per square meter. So either of the two yung gagamitin yung formula kasi the same lang. Example 3. A 25 kVA transformer has 500 turns on the primary and 50 turns on the secondary. The primary is connected to 3000 volts, 50 Hz supply. Find the full load primary and secondary currents, the secondary EMF, and the maximum flux in the core. neglect leakage drops, and no load primary current. So we have given apparent power is equal to S1, 25 kVA, N2, 50 turns, frequency 50 Hz, N1 is 500 turns. The V1 is 3000 volts. So this type of transformer is a step-down transformer because the number of turns in primary is greater than the number of turns at the secondary. So required is the primary current, secondary current, and the induced EMF at the secondary. Also the flux maximum. So this is our circuit diagram. We have here the turns at the primary, and this one is the turns at the secondary. Your I1, of course, is to the right. I2 is to the right also, going to the load. This is your input voltage, and this is your output voltage, V2. E1 is the induced EMF at primary, E2 is the induced EMF at secondary. So turns ratio A is equal to E2 over E1 is equal to N2 over N1. Solving your turns ratio is equal to 50 turns divided by 500 turns at the primary is equal to 0.1. Solving now your induced EMF at the secondary, E2 is equal to E1. 0.1 times 3000 volts is equal to 300 volts. Solving the primary current, I1, from our formula, apparent power is equal to E1 I1. So I1 is equal to 25 kVA divided by 3000 volts. That is 8.333 amperes. For E2, I2, from our formula in our first discussion, I2 is divided into I1, that is your turns ratio A. So I2 is equal to AI1 is equal to 0.1 times 8.333. So that is 0.8333 amperes. Solving now our maximum flux from our chapter 1, maximum flux is equal to the flux density maximum multiplied by the area of the transformer. So E1 is equal to 4.44 Fn1 flux M. So you can solve this flux M also at the secondary, that is E2 equal to 4.44 frequency N2. So flux M, maximum flux is equal to 3000 volts divided by 4.44 times frequency 50 times the number of turns at the primary 500. So flux maximum is equal to 26 milliweber or 0.027 Weber. 0.027 Weber.